Welcome to Op-Amp Stability Basics, Part 6. After completing this course, the learner will be able to learn the definition of non-loop stability problems, recognize the frequency of oscillation and occurrence can help debug an op-amp non-loop stability problem, apply a fix for oscillations due to an input bias current cancellation resistor, understand that PCB traces can become unwanted circuit elements that can cause unstable operation, learn how power supply connections through PCB traces and wires can create undesired oscillations. Recognize that a ground symbol on a schematic is not always the same ground path on a PCB, and apply a composite output stage fix to avoid oscillations on certain types of op-amp output stages. Non-loop stability problems are defined as those that are caused by a real-world PCB implementation of an op-amp circuit schematic, which is proven stable by simulation techniques, assuming accurate op-amp macro models. For non-loop stability diagnosis, it is important to define two key frequency points, FCL and FUG. FCL is the frequency at which loop gain goes to 1 or 0 dB. FUG is the unity gain bandwidth frequency of the op-amp. Answers to the key diagnostic questions will help determine the cause of oscillation. The frequency of oscillation should be noted as either less than FUG or greater than FCL. Check if the circuit oscillates when loaded or unloaded with a signal applied. Check if the circuit oscillates with Vin equals 0 volts. There are several non-loop stability problems that can have similar symptoms on a real-world PCB. By understanding the main causes of non-loop stability problems, a real-world PCB can be checked for each type of cause, and thus eliminate those that are not the cause, to leave the final one or ones that are. The Key Diagnostic Questions box is a shorthand reminder of key things to look for in a PCB implementation of a circuit that has oscillation issues. The detailed definition of each of these key questions are given here. FOSC less than equals FUG or FOSC greater than equals FCL means oscillations on the output can be less than or equal to the unity gain frequency, FUG, or oscillations on the output can be greater than or equal to the closed-loop frequency, FCL. Oscillates if unloaded means with no load on the output but for any value of the input signal voltage, Vin, does the output show oscillations? Oscillates with Vin equals 0 means with normal application load on the output, does the output oscillate when the input signal voltage, Vin, is equal to 0 volts? There is an established practice of always balancing the resistance on each input of an op-amp to prevent an offset voltage error due to input bias current flowing through different resistors. If not careful in PCB layout, this node can become a high-impedance node that picks up unwanted signals. Consider that many bipolar op-amps use input bias current cancellation techniques that keep input bias current IB low, and so an RB plus resistor may offer no significant advantage. JFET and MOSFET op-amp topologies have very low input bias currents. The input bias current out of the inverting input of the op-amp flows through a combination of RF in parallel with RI. This input bias current will create an additional offset voltage term, VOS_IB, on the inverting input of the op-amp, if RB plus is a short or 0 ohms. If the op-amp input offset voltage is equivalent or less than VOS_IB, then RB plus will not provide any significant improvement in total offset voltage error. If RB plus is necessary for the application, consider bypassing it with a 0.01 microfarad or 0.1 microfarad ceramic capacitor that will provide a low impedance path over frequency. The observed oscillation frequency if RB plus is used, and not bypassed with CB plus, can be between FCL and FUG. The op-amp circuit may or may not oscillate unloaded. The op-amp circuit may or may not oscillate with Vin equal to 0 volts. On PCB routing, it is critical to avoid routing output high current traces near high impedance input traces of the op-amp, as this can create coupling and positive feedback into the op-amp. Take care to route high current output traces away from input traces and route them in parallel with their return current path, either on the same or on an adjacent layer to form an equivalent twisted pair connection. The observed oscillation frequency due to poor PCB layout can be between FCL and FUG. The op-amp circuit may or may not oscillate unloaded. The op-amp circuit may or may not oscillate with Vin equal to 0 volts. Supply line connections can cause op-amp stability problems too. For op-amps driving capacitive loads, power supply lead inductance can interact with the capacitive load and form an LC tank circuit, creating oscillations. If there is excessive series resistance, RS, in the power supply lead, load currents can flow through it and cause a modulated signal to feed into the power supply pin. Most op-amps do not have a ground pin, and therefore rely on the power supply pins to be at good low impedance AC ground for connections of internal compensation components. The observed oscillation frequency, if there are unwanted impedances in the power supply lines, can be between FCL and FUG. The op-amp circuit will not oscillate unloaded. The op-amp circuit may or may not oscillate with Vin equal to 0 volts. Power supply line problems are easily mitigated up front by using good design practices. At the local PCB power supply connection point, low-frequency bypass capacitors, CLF, of 10 microfarads per amp-out peak of op-amp output current should be connected from each positive and negative power supply to ground. Often at this same connection point, a high-frequency bypass capacitor, CHF, of 0.1 microfarads will be put in parallel to help electromagnetic interference, EMI, and radio frequency interference, RFI, from coming into or going out of the PCB. At each power supply of each device, there should be a high-frequency bypass capacitor, CHF, of 0.1 microfarads directly at the IC power supply pin and connected to a single-point ground plane. Provisionally, if there are highly inductive power supply lines, a small value resistor, RHF, of 1 to 10 ohms may be placed in series with the CHF capacitors to avoid LC high-frequency oscillations. Ground loops can cause instability as well in op-amp circuits. But what are ground loops, and how do they create problems? Shown here on the left is an op-amp circuit, which includes the grounding schematic. RGY and RGX represent PCB parasitic trace resistance due to a daisy chain ground layout. As load current flows from the output of the op-amp through the load, RL, and back to the supply ground main connection point, it creates a voltage drop across RGX, which can then be seen as positive feedback to the op-amp and cause oscillations. In addition, the accuracy of the voltage across RL will be an error, since Vout is assumed to be driving a load connected to ground, and not through RGY and RGX to ground. The observed oscillation frequency for ground loops on PCBs can be between FCL and FUG. The op-amp circuit will not oscillate unloaded. The op-amp circuit may or may not oscillate with Vin equal to 0 volts. Fortunately, the solution is easy to implement by all connections returning individually to a single point or star ground. This solution is often implemented in good PCB designs using ground planes. One less obvious op-amp stability problem shows up in IC op-amps that use composite output stages. This is the one non-loop stability problem, where the frequency of oscillation is greater than the unity gain frequency. The op-amp circuit will not oscillate unloaded. The op-amp circuit will not oscillate with Vin equal to 0 volts. Shown on the left is an equivalent PNP output stage to sink current, used as an alternate to a high current PNP transistor. Since good PNP, high current transistors are often not readily available on a process, this stage uses an NPN high current device, driven by a low current PNP device. This composite output stage has local feedback and a bandwidth greater than 10 times the unity gain bandwidth of the overall op-amp. Under reactive loads, these stages are sometimes prone to high-frequency oscillations. The solution is the use of an output RC series snubber network directly on the output, as shown on the right. The output snubber network, RSN and CSN, lowers the high-frequency gain of the output composite stage to prevent unwanted oscillations.